Okay, hello everyone. Good afternoon, all of you. So we'll start with the quote today. It says by Suchita Gaur, life is a journey, not a race. It's not meant only to reach the finish line. It's meant to make every moment matter and count for a glorious life. So that is very important. So everybody has to have a goal, of course, but some people may reach goal or may not reach goal, and during the journey or while reaching the goal, all people they feel that they are struggling like anything. So that is not the way we have to live. We should not live with struggle. We have to be happy. Every moment we have to enjoy. We have to enjoy the journey. That is more important. Not reaching the destination, but every moment you have to enjoy the journey. Then life will be beautiful. And today is the birthday of who is the great person? Today's birthday. I think many people may got shocked to
Swami
see
Vivekananda.
Swami Vivekananda. Yeah. So Swami Vivekananda. Every word is so inspiring actually. If you read any sentence of Vivekananda, any speeches and all, every sentence is highly inspiring. So he says strength is life, weakness is death. Expansion is life, contraction is death. And love is life and hatred is death. He was a key figure in the introduction of the Indian philosophies of Vedanta and Yoga to the Western world and is credited with rising interfaith awareness, bringing Hinduism to the status of a major world religion during the late 19th century. So all people know that he is very famous with this speech, the first word, Sisters and Brothers of America. And when he went to the Parliament of Religions in Chicago for the speech, and when he has given a short span of time, and when he got up and just said Sisters and Brothers of America, and people started giving standing ovation for the whole time that is given to him. And later the time is extended for him. And he conducted hundreds of public and private lectures and classes disseminating tenets of Hindu philosophy in the United States, England, and Europe. In India, Vivekananda is regarded as a patriotic saint, and his birthday is celebrated as National Youth Day today. Okay, just if you want to see any scientist today, he is Lanoir. Have you heard about his name?
The solenoid cycle.
Yes, sir.
Yeah, Lanoir cycle. So what is the speciality of this? Anybody?
Sir, efficiency is equal to Carnot efficiency.
No. There are only two cycles for which efficiency is equal to Carnot efficiency. What are they?
Atkins.
No. Stirling cycle and Ericsson cycle. Okay, those two have the same efficiency as Carnot efficiency. All others have less efficiency only. And the specialty of Lanoir cycle is it has only three processes. If you see all cycles, heat engine cycles are having four processes or more than four. What is the cycle which has more than four processes?
Dual cycle.
Dual cycle, right? And Lanoir cycle has only three processes. And this is another important thing as I was telling about constant volume combustion. Okay. So other than Otto cycle, this also has constant volume combustion cycle. And this is the cycle which is used in pulse jet engines. As I was telling pulse jet engines. Okay. This is used in the pulse jet engine. Okay. He invented and devised the world's first commercially successful internal combustion engine. He moved to Paris, where his work with electroplating led him to the other electric inventions, among them a railway telegraph. Lanier patented his first engine in 1860, looking much like a double-acting steam engine. You can see that figure there. It fired an uncompressed charge of air and illuminating gas with an ignition system of its own design. One of these engines powered a road vehicle in 1863, another ran a boat also. Because of improved designs by Otto, at that time Otto cycle came into picture, and because of the other engines, the Lanier engine became obsolete and only about 500 Lanier engines were built. The Lanier engine wasn't efficient enough compared to Otto cycle, diesel cycle. And the inventor died poor. Okay, so that is an unfortunate thing. Though he's a big inventor and a lot of inventions on his name, but he died poor. Okay, today we'll continue having the review of thermodynamics. So last class we have discussed up to the first law of thermodynamics. So we have seen first law for a flow process. So generalized first law of thermodynamics we have seen for the flow process, and if it is for steady flow, then dCV by dt is equal to 0. Then we will get mq dot is equal to m dot into h2 minus h1 plus c2 square minus c1 square by 2 plus g into z2 minus z1 plus w dot. So like this you will get. And then we normally apply for various processes, and all of them are to be considered. But many times we make assumptions. Some of the processes, some of the terms will be negligibly small. If you take boiler, change in kinetic energy and change in potential energy will be negligible. If you take a turbine, again, there will not be any heat transfer. And if you take boiler, there will not be work transfer. If you take turbine and compressor, there will not be heat transfer. Like that, there will be. But what we do is we see the quantitatively, some are negligibly small. Okay. And if you, that's why normally if you see, if Rankine cycle, if you take heat transfer, we take change in enthalpy. Work transfer, change in enthalpy for each process, turbine and pump and compressor, like that. Okay, so in that way, we can apply this to the various processes. And coming to the limitations of first law. So first law will not talk about the quality of energy. Okay, so we say some energies are high quality and some are low quality. So which are high quality energies and which are low quality energies?
Low quality energy is like heat,
Yeah,
whereas work is high.
yeah, heat is low quality. And work, potential energy, kinetic energy, these are all high quality. So all high quality energy can be converted to low quality energy, but all low quality energy cannot be converted to high quality energy. There we have to lose some of the heat. Okay, that's what the second law says. And also it talks about the direction of the process. Right, whether suppose it is like a cup can fall and break into pieces, but all the pieces cannot become a cup. Okay, so other process we know that it's not possible. In that way, suppose something is burnt, we will get the heat energy, but using heat energy we cannot create the chemical component. Okay, so our fuel we cannot get it back. So in that way, there is a direction of the process and there is a quality for the energy. These are the main two things. And these are given by two laws. Okay, one is Kelvin-Planck statement. So what does it say? There cannot be a device which produces or converts all the heat energy into work energy. So that is something like if I put a heat engine here and if I put a high temperature reservoir. So what is the characteristic of a reservoir?
Set temperature remain constant.
Yeah.
Infinite specific heat.
Yeah, infinite heat capacity. Okay, so temperature will be constant for whatever heat transfer. Like that. So high temperature reservoirs are called as
Source.
sources. Examples?
Sun.
Sun.
Yeah, sun, stars, all those things. And practically,
Furnace.
boiler, furnace, combustion chamber. Okay, all these things are sources. Okay, these are high temperature reservoirs. And low temperature reservoirs, these are called
River.
sinks.
Sink.
What are they?
River.
Yeah, rivers, seas, atmosphere. Okay, all these are sinks. Okay, so if there is a high temperature reservoir giving a heat of QH, and if it does work W like this, so this is not possible. That's what he says. This is what is called as Kelvin Planck violator. And this is also ppm of second kind. What is ppm? Perpetual motion.
Perpetually motion machine.
So this is Kelvin Planck violator. So which converts all the heat into work. That is also it has what is called, because efficiency is equal to work by heat supplied. So this will be 100% here, which is not possible. So the practical cycle will be, so I should have a high temperature reservoir, I should have a low temperature reservoir, and I should have a heat engine which taking QH, and some should be lost by QL, and this should be W net. And by first law of thermodynamics, this is equal to QH minus QL. So the efficiency is equal to W net by QH, or QH minus QL by QH, or 1 minus QL by QH. Okay, so this is the heat engine. And similar to that, we have what are called as refrigerator and heat pump. Okay, what is the difference? So if I draw here like this, like this, is it a heat pump or a refrigerator?
So we can't say unless we have the focused area.
So whether this is getting cooled or this is getting heated. Okay, so what actually the need, it depends on that. If this is room and if this is atmosphere, now can you say what is this?
Refrigerator.
Refrigerator or air conditioner, right? So if this is the room and this is atmosphere, because I am taking heat from the room and heating the heat from the atmosphere and heating the room, this is heat pump. Okay, so we define instead of efficiency, we have to say COP. COP is equal to here of refrigerator is equal to
TL upon TF minus T.
So what is needed is QL and what is spent is W, right? So this is equal to QL by, because W is equal to QH minus QL. So QL by QH minus QL. Similarly, if you take COP of heat pump, here the need is QH by QH minus QL. And we know that COP of heat pump minus COP of refrigerator is equal to 1.
1.
QH minus QL is 1. And so that is about refrigerator and heat pump. And the other statement is
Lassier statement.
Lossless statement.
What does it say?
The device cannot transfer heat from low to high temperature without absorption of any work output.
So this is not possible. Okay, this is what is called as Clausius violator. If this is to happen, I have to spend some work so that I can transfer this here like this. Okay, so this is Clausius violator and this is possible. And later we can show that both are statements are equivalent. So when I am talking about ppm, okay, ppm2 is kp violator. So how will be ppm1?
So if we do not provide any heat, still we can get work.
Yeah,
And-
without any transfer or giving any energy, it produces positive work. That's all. Okay. So nothing is given. So if you take, because delta Q is equal to du plus delta W, so this is 0. And if you want delta W is to be positive, this is minus du. So work can be obtained by spending energy. So it is producing work means its energy is lost. If U is decreasing, temperature is decreasing. So it cannot decrease below the atmospheric temperature without any doing anything. So I can work only up to some time. Okay. So as long as my internal energy is lost. And after that, I cannot do any more work. This is what is called as ppm of first kind. And anybody knows ppm of third kind?
Absolute zero.
Any machine involving movable parts and lacking the friction.
Yeah, which runs continuously without input and even output also. There is nothing like output and no input also, but it runs, which runs continuously. So that is ppm of third kind. So people came with actually many different devices. Okay, so and sometimes people cheated other people also that it will work. That is keeping some motor outside and it will be continuously running. We won't see the motor, but logically they explain how it works and all. Okay, there are many videos if you see in the YouTube perpetual motion machines, you can see some of them, and it will be so surprising. Okay, and then coming to what is called as Carnot cycle. Okay, which is completely, this is the only reversible cycle. And so the efficiency of Carnot cycle is 1 minus TL by TH. So for Carnot cycle, for any cycle, 1 minus QL by TH. But for Carnot cycle, it is 1 minus TL by TH also. So QL by QH is equal to TL by TH for Carnot cycle. And another thing is there are what are called as corollaries. Of Carnot theorem we say. Okay? Because what Carnot theorem says is reversible cycle has the maximum efficiency. Okay, so what are the corollaries?
Having maximum efficiency and for a given temperature it has same efficiency.
All reversible cycles working between TL and TH, okay, same reservoirs will have same efficiency. Okay, or no other cycle okay, you have more efficiency than. And okay, another thing is it is the efficiency is independent of the
Working fluid.
Working fluid.
working fluid because it depends only on the reservoir temperatures. Okay, and here, so for a reversible cycle, because QL by QH is equal to TL by TH, so our sorry, so QH by TH minus QL by TL equal to 0. And so another thing is any reversible cycle can be converted into number of Carnot cycles. It is something like if I have a cycle like this, so I draw isentropes, and between everywhere two isotherms if I draw like this, so that the area will remain same. So each is a Carnot cycle, and it will be split into number of Carnot cycles like that. So for any cycle, because for each Carnot cycle, if I write delta Q and delta Q, a small cycle, so this will be right. So, and if I sum up them, then integral delta Q by T will be equal to 0 for any reversible cycle. And this is what is called as, what is this?
Clausius state.
Clausius inequality.
Clausius theorem. And this is also called as mathematical expression for second law of thermodynamics, the Clausius theorem. So if you see, first law is given by integral delta Q minus delta W equal to 0, right? Which came with delta Q minus delta W is equal to D of internal energy like this. A new property came into picture. So whenever a cyclical integral of some integrand is equal to 0, this can be written as change of a property. Now coming to the second law, which is given by Clausius theorem, where integral delta Q by T is 0 for reversible cycle. So this delta Q by T can be written as change of some property. We call it as entropy. Just in similar way. So this is the way the entropy comes into picture mathematically. And if you come to for irreversible cycle, because if you see efficiency of irreversible is less than efficiency of reversible, and efficiency of irreversible cycle is 1 minus QL by QH, and the efficiency of reversible cycle is 1 minus TL by TH, and the 1 and 1 if I cancel, and this minus if I take out, it will become greater than. So QL by TL is greater than QH by TH, or QH by TH is less than QL by TL, or QH by TH minus QL by TL is less than 0, or integral delta Q by T for irreversible cycle is less than 0. And if I combine Clausius theorem for reversible and irreversible cycles both, so delta Q by T is less than or equal to 0 for any cycle. So reversible equal to irreversible less than. Okay, and this is called as Clausius inequality. Am I right?
Yes.
Okay. So here again, integral delta q by 2, delta q by t. Okay, that is for a okay. Okay, delta q by t and irreversible, and delta q by t reversible if I write, which will be more and which will be less. Irreversible is less than 0. Reversible is equal to 0.
Reversible will be more.
Yeah, so irreversible is less, right? And delta q by t reversible is ds. So this comes with ds is greater than delta q by t for a irreversible process. So ds is equal to delta q by t for reversible. ds is greater than delta q by t for irreversible. So combining them, ds is greater than or equal to delta q by t for any process. Okay, so from this we get what is called as law of increase of entropy. Am I right? So if you take universe is what type of system?
Isolated.
Isolated system. So for universe, delta q is
0.
0. So ds is greater than or equal to 0 for a universe. Okay, so there will be so many things happening here, and we know that all real processes are irreversible.
Irreversible.
So for anything what is happening, whatever is happening, so there will be increase in the entropy. Okay, so if I read, I talk, I speak, I walk, okay, whatever I do, I eat, okay, I study. So for every action of everybody, we are contributing in the increase of entropy of the universe. Am I clear?
Yes, sir.
Yes, sir.
Okay, so this is called as the law of increase of entropy. And okay, delta q is equal to, we know that du plus pdv, right? And delta q also, okay, du plus pdv. And delta q is equal to tds for reversible process. So I can write TDS is equal to du plus PdV. And this is important. Here, delta W is equal to PdV for quasi-static process. And delta Q is equal to TDS for reversible process. Okay, so if I write this, this is only for reversible process, this is right. Okay, so we feel like that, but actually this is true for any process. Why?
All are properties.
Yeah, because all are properties here. So I derived it for, suppose, a reversible process, but this is true for any process. Like as I told, du is equal to cv dt. Okay, it is not only for constant volume process. This is true for any process. In the same way, this is true for any process. In the same way, because h is equal to u plus pv, dh is equal to du plus pdv plus vdp, and du plus pdv is equal to dh minus vdp. So I can write this as dh minus vdp also. So these two are called as TDS relations, which are valid for all processes. Am I right? which are valid for all processes. And from these relations, we can derive the change in entropy for any equation. So we will get TdS is equal to du plus PdV. If I divide by T, so this will become CV dt by T plus P by T is, because PV is equal to RT, I will write RT dV by d. P by T is equal to, P by T is equal to R by V. R by V dV. Okay. Okay, just I will write. Like this. And here also we can, from the other relation, dH minus VdP, I can write ds is equal to Cp dt by T minus V by T dP, that is equal to Cp dt by T minus V by T is R by P dP by P. So if I integrate it, S2 minus S1 is equal to Cv log T2 by T1 plus R log V2 by V1, or here S2 minus S1 is equal to Cp log T2 by T1 minus R log P2 by P1. And combining these two, we will get other relation also. Say S2 minus S1 is equal to Cv log P2 by P1 plus Cp log V2 by V1. This also you will get. Okay, these are the three relations which give me change in entropy. Okay, and here we come to what is called as the third law of thermodynamics. What is the third law of thermodynamics?
Absolute zero temperature cannot be achieved in.
So it gives the
finite number of
it gives the reference state for entropy. Because I got only change in entropy, if I want absolute entropy, we have to give some reference state. So we take S is equal to 0 at T equal to 0. Okay. So another thing is what it says is we can never attain absolute zero temperature. Okay. Actually, Kelvin Planck violator also says like that. Okay. So suppose if
Heat rejection will be zero.
yeah, heat rejection is 0 means it is like T equal to 0, right? So it violates the second law, right? It becomes violator. So we can never reach T equal to 0. So this is another thing. And if you see general entropy balance law, like energy equation, we have entropy equation also. If you take an open system, okay, a control volume like this. So we get the change rate equation. Always we are interested in rate equation. And DSCV, the change in rate of change of entropy of a control volume is equal to
entry entropy minus
entering and something leaving. Okay, sigma m dot I SI minus sigma m dot E SE. Okay, some entropy is entering and some entropy is leaving. For whatever enters, there will be increase in the entropy. For whatever leaving, there will be decrease in the entropy. Plus
net change within the series.
Q dot sigma Q dot by T. And plus Sgen. This is the entropy generation. For every heat transfer, there will be increase in the entropy, and there will be some entropy generation. Okay, so if it is steady state, again this will be equal to 0, and Sgen you can get as sigma m dot ESC minus sigma m dot ISI minus sigma q dot k, some q dot k by tk, like that. That is the heat transfer at a particular temperature, like that. Okay, this is the entropy balance equation. Okay, these cycles. This is steady state. Okay. Anything else we can discuss? Okay, then we talk a little bit about what is exergy. So what is exergy? This is also called as available energy.
Maximum amount of what we can extract.
Yeah, that is W max. Okay, this is also equal to maximum work. That is, if you have, it is something like Carnot work also. If I have a heat source, and if I can have a Carnot engine, whatever work that can be developed, that is the maximum work. But it need not be only heat source. I can have, if I have potential energy, the complete potential energy is available energy only. If there is kinetic energy, the complete energy is available energy only. But if I have heat energy, then all the heat energy is not available energy. Okay, it is something like, if I take efficiency of Carnot cycle, W by Q. Okay, and this is also equal to 1 minus TL by TH. Okay, and so what is the maximum work I can get? So when high temperature reservoir is there, if low temperature reservoir is atmospheric pressure temperature, that is the maximum thing I can get. Okay, it is something like, if I have a heat source at this, and if I have sink at this temperature, then this is the work I can get. But this is not the maximum work that is possible. Possible is if I can have Carnot cycle up to atmospheric temperature. Okay, so this is all what is called as available energy, and this is unavailable energy. And this is available energy.
Sir, all high grade energy equal to available energy, can we say?
Yeah. All the high grade energy is available energy. And so here W is equal to 1 minus T naught by TH into Q. Okay, so this is again availability. If I have a heat source at temperature TH, and if there is heat transfer Q, then the maximum work is 1 minus T naught by TH into Q. Okay, and here available energy is different and useful energy is different. Okay, so Carnot work is the maximum work, but suppose if I have a another cycle which gives me less energy. Okay, so that is what is called as irreversibility. Irreversibility is equal to the maximum work minus useful work. Okay, this is the maximum work that is possible, because I know that Carnot cycle is not possible, so I cannot get W max. Only out of that, only some useful work is only W useful, and this is called as irreversibility. And so if you take the first law efficiency, which is equal to W useful by QH. Okay, for any cycle, some W useful is the output that I am getting. And the Carnot efficiency is W max by QH. And so here, what people say is, there is no use of having first law efficiency, they defined what is called as second law efficiency. So what it says is, I cannot, there is so much of QH is available, and if I get some useful work, and you cannot say I am only this much of efficiency, my efficiency, because maximum work that is possible, with that you compare. Okay, so I am getting some useful work with my cycle, and the maximum work possible is this. And with this I can compare, but not with QH. That's what people say if you want to know the efficiency of a particle cycle. This is what is called as second law efficiency. Am I clear?
Yes, sir.
So this is nothing but W useful by QH by W max by QH. And W useful by QH is first law efficiency. And W max by QH is Carnot efficiency. So this is the way these two are related, second law efficiency and first law efficiency. So second law efficiency is less or more?
More, sir. Compared to
More,
first,
it will be more. Okay. So if you calculate with QH, it will become less. But because it is like relative grading, right? You cannot compare your marks are only 60. Because the first mark itself is 65, you cannot tell that my efficiency is 60% only. I have to compare with the first person in the class. So that is the maximum possible marks that a person can achieve. Okay, like that. So if my father used to scold me, you got only 98, what happened to those 2 marks? And I told the next mark is only 80 marks. I have a lot of high marks I got, but he was never satisfied. He told those 2 marks are lost, so you don't know 2 bits or something. So like that. So I'm not happy, because if I can compare with the other people around me, then I will be happy. Okay. So like that. This is that's why second law efficiency gives a better understanding of the relative performance of a particular engine. Okay, this if you see the back thing, so the okay, that's one thing. So here there are some things like XSG of a open system or closed system. Actually, this is defined as H minus H naught minus T naught into S minus S naught plus V square or C square by 2 plus GZ. Okay, this is the maximum available energy, right? And this is given by psi. Okay, this is XSG for a open system, and for a closed system, people define as phi. Phi is equal to U minus U naught minus plus P naught into V minus V naught minus T into S minus S naught. Okay, so if it is going from one state to another state, so what is the maximum work that is possible is psi 2 minus psi 1, like that. Okay, this much of available energy at 1, and this became the available energy at the 2. So this is the maximum work that is possible. So this will be equal to H2 minus H1 minus T naught into S2 minus S1, like this. Similarly, for the closed system, U2 minus U1 minus T naught into S2 minus S1. Okay, from this, actually, there are 2 properties people have defined, what is called as Gibbs function, and from here, Helmholtz function. And Gibbs function says G equal to maybe H minus Ts. So it will become like availability, like that. So this similarly, Helmholtz function, sometimes people write A, U minus Ts, like this. Okay, and here exergy balance also you can write like entropy balance. And only main thing for every process, one thing you have to remember that there will be some entropy generated, and at the same time some exergy is destroyed. Okay, that is opposite things happen because available energy is lost. So there will be always entropy generated or exergy destroyed. So whenever there is a process is taking place in the universe, that is a reversible process. Okay, so here it is something like rate of change of, again, rate equation if I write. So this is equal to 1 minus T naught by Tk for every heat transfer like this, and minus W minus again okay. So this is the exergy balance equation. If there are any heat transfers, this is due to which there will be change in the increase in the exergy, and this is also increase the exergy because work done by the system. And this is exergy entering, this is exergy leaving. This is for, again, general statement. And again, steady state means dx/cv by dt equal to 0. And you can find out what is exergy destroyed by taking all the other things to the other side. Okay. So in this way, you have the exergy balance. Anything else? Okay, just hold the time. Okay, then it is just a quick revision of all the things, and the remaining things, cycles and other things, I think you are familiar only. Otto cycle, diesel cycle, Joule cycle, Ericsson cycle, Stirling cycle, all these things you have to be quick enough. Okay, one general thing I will tell you. A general heat engine, okay, in general I am telling, again, there will be small expressions. There will be minimum of 4 processes. Again, as I told, there will be Lenoir cycle like thing may be there. Okay, so usually 4 processes. Why? Because there should be heat addition, because heat engine heat is converted to work. Okay, there must be heat addition which is to be converted to work. This must be there. Okay. And then there should be heat rejection. Why?
Second law of thermodynamics.
Second law of thermodynamics is there. And there should be positive work. Okay. So because heat is converted to work, so there should be some positive work. And this always will have some expansion. Positive work will always have expansion because PDV. Okay. So expansion will be there. So whenever there is an expansion process, to complete the cycle, so there should be compression. Right? So one expansion process, one compression process, one heat addition process, one heat rejection process should be there. Okay, sometimes 2 processes may take place only in the single, 2 things may take place in the single process, like a Lenoir cycle. It may happen like that. Or there may be, for heat addition, there may be 2 processes, or there may be work done maybe in 2 processes like that. We can have more than 4, definitely, and sometimes less than 4 also it can happen. But these 4 things should happen. There should be heat addition, there should be heat rejection, there should be work done or expansion, and there should be compression. Okay, so these 4 should take place in any heat engine. Am I right?
Yes, sir.
Right. So for every cycle, we have to know about it. Whenever there is a work producing heat engine is there, I have to know what are the components for this, so where it is happening like that. Okay, so these things should be there. Okay, now we will quickly see about the simple Brayton cycle, what we have done. So we have compressor. So expander and compressor is there. So heat addition is there. And heat rejection takes place here to the atmosphere. Okay, so this is combustion chamber. And this is run by this. And here work produced. Okay, so here WC is given to it. And this side we get WT minus WC. And QH is here. And QL is lost to the atmosphere. So we got like this 1, 2, 3, 4 WC, WT, QH, so QL. So we have found out the expressions. We got efficiency as 1 minus 1 by C, where C is equal to R power gamma minus 1 by gamma, and R is equal to P2 by P1 or P3 by P4. And then we have T is equal to T3 by T1 or T max by T min. And we got the work is equal to W by non-dimensional work, W by CPT1 as T into 1 minus 1 by C minus C minus 1. This is W turbine and this is W compressor. This is W net by CPT1. And we have seen that if you draw graphs, so we got like this. If this is R and this is efficiency, right? This is 1. And for different values of gamma, we got like this. And if you take W by CPT1, W net by, and we get 0 at 2 points like this. So here and here, this is C max is equal to T. And here C optimum is equal to root T. And we got like this with the values of T. Okay, this is the way we got. And we got C optimum as root T, right? And so at this particular point, we found that T2 equal to T4. So we found these extreme cycles. So one is, it may go like this and come back. This is one extreme. And if this is metallurgical limit, the other extreme is it may compress like this and come back like this. So the optimum efficiency we get when this 2 is equal to 4. Okay. Could you recollect all these things? And so, as I told, because of that, people thought about what is called as heat exchange cycle or regenerative cycle. So what we do is compressor I have and combustion chamber I have. And this exit from the turbine, it will be exit from compressor, it goes like this and goes like this, and exit from this, it goes like this. This is heat exchanger or regenerator. Okay, and okay, this is 1, this is 2, and this is 3, and this is 4 as usual. So if the pressure ratio is less, actually T4 is greater than T2 if R is less than R optimum. Am I right? Yes. So here, from here to here, there will be heat exchange process, and here only there will be combustion. Okay, so what I do is I will name this as some 5 and name this as 6. Okay, 1 to 5, it comes with 5. In the heat exchanger, it picks up heat and comes out with 5, and 5 to 3, it gets heated in the combustion chamber. Am I clear about this? And from T4, it goes to the heat exchanger, it comes out with 6 at low temperature. Now heat loss is only this much. Okay, this is given in the heat exchanger. Okay, so we'll write like this. Heat exchanger, this heat goes into this. Is it clear?
Yes, sir.
Okay, here can you tell me what is the effectiveness of heat exchanger? Epsilon is equal to
T5 minus T2 upon T4 minus T2.
the
T5 minus T2 by T4 minus T2.
yeah, T5 minus T2 by T4 minus T2. Okay, if effectiveness is 1, then T4 equal to T5. That is, it can be heated up to T5. But usually it goes something like this. It will be less than that. Okay, in real cycles. But in ideal cycle, I can assume that it is heated up to T5, T4. Okay, so now will there be any change in the output?
No, sir.
Input.
Okay, turbine compressor work are not changed. What is changed then? Heat input is changed.
Heat input changes.
So what is heat input?
T3 minus T5.
Yeah,
CP
CP
into T3 minus T2.
minus T5, which is also equal to CP into T3 minus T4, which is also equal to WT. Am I right?
Yes, sir.
Okay. Now, if I okay, if I take the efficiency, now actually W net by CPT1 is same thing, T into 1 minus 1 by C minus C minus 1. Okay. And so efficiency is equal to W net by QH, right? And W net is T into 1 minus 1 by C minus C minus 1. And what is QH, which is equal to W turbine? So if I divide this by CPT1, divide this by CPT1, what is non-dimensional turbine work? T into 1 minus 1 by C.
Sir,
Am I
this
right?
work done, sir, this work done expression is for R optimum, na?
No, no, no,
Here
no.
are-
No. It is not for R optimum.
Okay, sir.
For R optimum, you know why actually I didn't do that. So for R optimum, C is equal to root T, right?
Oh, yes, sir.
So T into 1 minus 1 by root T minus root T minus 1. Okay, I will do that here. So what happens? This is equal to T into root T minus 1 by root T minus root T minus 1. So what will happen here? So this will become root T. Root T into root T minus 1 minus 1 into root T minus 1. So this is root T minus 1. If I take common, again root T minus 1 will be there. It will be like this. Am I clear?
Yes, sir.
So this is actually T3 by T1 minus 1 whole square. And so root T3 minus root T1 whole square by T1 is equal to W net by CPT1. This is max. Okay, if I cancel T1 and T1, W net is equal to CP into root T3 minus root T1 whole square. if I have maximum temperature and minimum temperature, the maximum work that can be done is this. Is it clear?
Yes, sir.
Yeah. So now coming to the heat exchange cycle, it comes like this. So this will be 1 minus C minus 1 by T into 1 minus 1 by C. If I simplify, what happens? Here,
By T.
yeah, T into C minus 1 by C. C minus 1 equals 1 minus C by T. Okay, this is the efficiency of heat exchange cycle. Okay, so if I draw again the variation of work and efficiency, variation of work is same as simple cycle. You will not get any change. But if I draw the efficiency variation, and if I put C here, and theta is equal to 1 minus C by T. Okay, so if C equal to 1, what is theta?
1 minus 1 by T.
What is T? T max by T
By
min.
T min.
So 1 minus T min by T max. What is this?
Carnot efficiency.
Carnot efficiency. Okay. So this efficiency is equal to Carnot efficiency. So suppose if I have again 1200 T3 and T1 is 300. Okay. And what is Carnot efficiency? 1 minus 300 by
75%.
75%. So if I take like this, so it starts with 75%. Am I clear? And as C increase, what happens to this? I am doing for T equal to 4. Okay. As C increase, what happens to efficiency?
Decreases.
Efficiency
Decreases.
decreases. Okay, that is important thing. For simple cycle, it increases. Okay, so actually for simple cycle, if it is like this, it decreases and decreases, and when C equal to root T, okay, what is the efficiency? 1 minus 1 by root T, right?
Yes.
And it becomes 1 minus 1 by C, which is simple cycle efficiency. So it decreases and decreases. At optimum pressure ratio, it reaches this. Am I clear? And if C increase further, then my efficiency will be less than simple cycle. Why my efficiency becomes less than simple cycle if I have heat exchanger?
In the heat exchanger, reverse process will be.
Yeah, what happens is, so here, if pressure ratio is less, it is okay. If pressure ratio is more, where is this? Okay, if pressure ratio is more, if I draw this cycle, okay, something like this. Okay. And what happens is, no, not like this. Something like this. This T2 will become more than T4. T2 becomes more than T4. the compression ratio is more, right? So there will be more exit temperature of the compressor. Then what happens? It loses the heat. Am I clear? My
Yes, sir.
exhaust temperature is less. My compressor temperature is more. If I want to heat it, actually I'm cooling it instead of heating. So if T2 is greater than T4, there is no use of heat exchange. I lose heat. Okay. So the efficiency will be decreased. So I should not have only in this region only I can have the, okay. So another thing is if suppose T is equal to 5, that is I have 1500 maximum temperature. So what happens to the Carnot efficiency? One minus 300 by 1500. Okay, that is 1 minus 1 by 5.
80.
80%. Okay, so it starts from 80%. And again, it comes like this. So in that way, I can have different values of T. I am going to have this. Is it okay? Any
Yes,
doubts?
sir.
Okay, so I think we can stop here. Okay, so this is the way our heat exchange cycle works. So next what we are going to do is, so the pressure ratios are high. So I have to go for multi-staging. And if you remember in reciprocating compressors, have you studied reciprocating compressors?
Yes, sir. Yes.
There, if I have multi-staging or large pressure ratio, so what we do, we divide them into stages, and in between what we do,
Cooling effect.
Intercooling, sir.
Cooling.
we put intercooler so that the initial temperature for each compressor can be reduced. And because the compressor work depends on the initial temperature, if that is less, my compressor work gets reduced. The total compressor work can be reduced by having number of intercoolers in between. Okay, that's what people thought about it. When I have number of axial flow or centrifugal flow compressors, here also if you can assume some intercooler in between, can we reduce the work or not? So that we will see in the next class. Even in the same way, expansion also can be divided into number of stages, and in between I can use reheater like intercooler here. So can we increase the work there? So these things we discuss in the next class. Any questions? Okay. I'll stop recording first.